All right. So thanks to everybody for joining the Corundum developer meeting today. Today I've got a few status updates, and yeah, let's go ahead and get the ball rolling here. Okay, so let's see, brief overview of what I'm going to be talking about. So I've been working over the past couple of weeks on putting the documentation together. Starting to look pretty good, but still needs a bit more work. Hopefully I'll get that presentable this week, and then we can continue hammering on that, you know, as modules are written and whatnot. So yeah, I'm moving up variable length descriptor support, or at least a part of it, to try to get some of that squared away, or some portion of that squared away sooner rather than later, at least, so we can get some components of that operational on the driver side. One thing that I came up through some discussions with Kent is that it might be useful to have some layer 2 processing built into Corundum as well. So if you're not hooked up directly to Ethernet Max, you can handle things like frame check sequences and whatnot. So talk about that a little bit. I'm also going to try to get some basic queue selection logic working that can combine what the application wants with what RSS with the RSS hash computation. So got a couple of points on that. I've also been taking a look at the management softcore and kind of how that's going to be integrated into the rest of it. I haven't done much implementation work on this, but I do have some ideas for kind of what that might look like and what core I'm going to use and whatnot. So yeah, we'll see. And then the PHY status registers and the GTYPLLDRP connections. Currently working on that. And I think I've changed a couple of things in terms of kind of my approach for that. And then also the 10G25G switching, just, updates on that. All right. So the documentation, I'm using Sphinx. I've imported a bunch of stuff from the README and the wiki and brought a couple things up to date. I've added documentation for all of the register blocks, and I'm working on adding documentation for a bunch of the modules. So right now, I think I have like kind of the main core modules in there with some basic documentation about all the parameters and ports and whatnot. Um, I think I'm not going to document all the modules from the get-go, but just the important ones that you need to know if you're integrating Corundum into a design. And then because there's a bunch of changes that I'm going to be making to some of the other modules, so it doesn't make too much sense to document them as they are now if I'm going to be going in and reworking a bunch of stuff. So status on that, that's in progress right now. Hopefully I'll be able to get this into a more finalized state later this week. All right, variable length descriptor support. I put this slide up a few times, but the idea is to kind of change the descriptor format such that we can get a number of benefits, including performance benefits over PCI Express, lower latency because of descriptor caching and read ahead and things like that. So the initial step that I'm going to do for this is effectively to move over to using the new descriptor format without fully implementing it in the hardware. So the idea here is currently the first 2 bytes of the descriptors just coincidentally are not used by the hardware or by the driver, and those are the bytes I'm going to use for the descriptor header. So I'm going to update the driver to write out the correct descriptor headers for the variable length descriptors. And then I need to update the queue pointers to operate in terms of blocks instead of in increments of descriptors. So effectively, it'll look like we're using the variable length descriptors from the standpoint of the hardware. And this will be a good stepping stone because then I can start getting the descriptor parsing logic and whatnot operational on the FPGA, and I won't need to, I can kind of test things out beforehand and be confident that that things are going to work. Yeah, so that's first pass, and then once this is operational, then the driver is going to be closer to what it needs to be in terms of how the queue management logic is implemented. And then second pass, I'll implement the actual parsing logic on the FPGA to handle these and get everything up to date. So it shouldn't take too long to get this first step set up. I'm not sure about the the final implementation of the the full variable length descriptor support, but we'll see. All right, so after talking with Kent and how he wants to take Corundum and attach it to effectively a switch port instead of a Mac, that got me thinking about a couple of things. And one thing that I've actually been thinking about for a while is PFC support for RDMA. That's kind of an important component, but my Ethernet Mac modules right now don't support PFC. So there's a question of, where would that logic have to sit? Would I add it to the Macs? Should it go in Corundum somewhere? Not sure what makes the most sense. That's kind of been on the back burner for a while. But after talking with Kent, it's like, okay, maybe there's a use case for being able to do some additional layer 2 processing, such as, frame check, sequence, insertion, and removal. If you're talking to a switch instead of a Mac, maybe you want to insert the FCSs because the switch logic leaves the FCS onto the packet. So what I've gone ahead and done is I've added some placeholder modules in Corundum, effectively right next to where it connects to the Macs, where this type of logic can be implemented. So right now I haven't actually implemented any of this stuff, but I have the location in the data path in the modules where we can do that. The one thing I might implement in the near term is some padding support, because the Xilinx CMAC modules for 100 gig don't like it if you give them a packet shorter than the minimum frame size, and they don't do any padding internally. So I have these CMAC pad modules in the kind of FPGA.V top level designs that are connected to the CMAC instances that pad frames out to 60 bytes. So what we can do is, we're not going to move those modules specifically, but implement some padding logic inside of Corundum, so we can enable that and pad the frames in Corundum before they're handed off to the CMACs, and then we can remove those CMAC pad modules. So that'll simplify things a little bit for the 100 gig designs. And another thing I should mention is that my Macs handle the FCS and they handle the padding, but that's not necessarily the case for all Macs. Ostensibly, that's kind of the job of the Mac. So you would hope that all Mac modules would do that, but potentially you can run into instances where that's not the case. So having this available in Corundum and having parameters to turn it on and off, I think would be a useful feature. So that's something that I'm hoping to accomplish in the future, and we now have placeholders for that to make that easier. All right, so queue selection logic. The folks at MLE were asking about this. Instead of having to modify the core logic to pick what queue they want, can they just indicate that from the application section? And this is something I've been mulling over. What I need to do is write the register interface basically for this, and a little bit of glue logic to make it work correctly. But the idea is to combine the TID TDEST values on the AXI stream connection from the application section on the receive path with the computed RSS hash. So the goal is so that software, controlling the driver has ultimate control over which set of queues are used. So we have to be able to kind of restrict what the application module can do, and also restrict what RSS can do, but combine these in a way that we can kind of divvy up the all of the queues into here's what this port can use, here's what that port can use, here's what the application section is allowed to do, based on how many queues are enabled and whatnot. So my thought is to do this in a pretty simple way, where we can take the TDEST value from the application and mask that off with a bit mask. And then we can take the RSS hash, mask that off with a bit mask, and then take an offset and add all those up, and that'll give you the destination queue ID. So in this way, you can offset each port by a fixed amount, and then you can provide sort of a little window that the application logic can use and that RSS can use to determine the queue. And the idea here is, how does TID fit into this? Well, we have a different app mask, RSS mask, and offset based on the TID. We have different registers for that, and the TID is set based on which port the packet entered through. So this allows you to make that lookup and do something based on the port. So this is also assuming that the application logic doesn't change the TID, which, I mean, if application logic changes the TID, then I guess it's now going to be seen as coming from a different port, which is, ultimately not really a big deal. Right. So the status on this is I am taking a look at where this is going to sit in terms of the implementation, and I'm probably going to have to add a slightly more extensive RSS related register block to handle all this stuff. But shouldn't really be a big deal. So I'm going to work on that over the next week or two, and we'll see what that looks like. All right, so the next component that I've been mulling over is the management Softcore. And the idea here is to put a RISC-V CPU core on the FPGA that can handle board and device specific functions. And using this, we can present kind of a unified interface to the driver that's going to be the same across, multiple different boards. The idea being that we can remove all of the board specific code from the driver, and then we can get we can use these features from both the kernel driver as well as the DPDK driver and the user space tools and whatnot. As of right now, for instance, all of the I2C stuff uses the kernel's I2C subsystem, and you don't have that available in the DPDK driver. So if we can push all of that into a softcore on the FPGA, then ostensibly any of the drivers should be able to take advantage of that. Right. So for API, what I'm planning on doing is kind of presenting at least 3 different levels. So the low level access would be, essentially direct access to whatever the interfaces are. So for like the transceivers, you can just do direct register access. You can read and write, specific registers on specific transceiver instances to change whatever setting that you want. So using this, you can do like board level diagnostics, or for I2C interfaces, you can, perform arbitrary reads and writes. You just specify which interface you want to use and which bytes you want to read or write, and then, it'll do that. But this is going to be very board dependent, right? Because you might have, different FPGAs will have, different register layouts for the transceivers, right? Intel and Xilinx devices are quite different with regards to that. Different boards have different setups on the I2C buses. Some use muxes, some use multiple I2C buses, things like that. So this one can be kind of board dependent, and that's not such a big deal to deal with that in the user space tools for low level diagnostics. But one level up would be, kind of a medium level operations. So these are a little bit more abstracted, potentially getting a little bit board independent. So the idea here is you might be able to, read some bytes from the configuration EEPROM, for example. So where that EEPROM sits is board dependent, but being able to read and write that is, in a general way, could be useful. And then, for instance, a high level one that sits on top of that could be, okay, give me a list of the assigned MAC addresses, and maybe those are read out of the board EEPROM, maybe they're read from a another microcontroller or something sitting on the board. So depending on the design, there's a couple of options there. And that can be abstracted inside of the firmware running on the software. And let's see. So another thing that you could do at the high level is you can have commands for changing the PHY link speed, things like that. And then the core would, handle all of the appropriate operations, including writing all the registers over the DRP interfaces to the transceivers. And you can even do things like changing CDR settings in the optical modules of I2C, kind of all at the same time with one, high level command from the driver. So I think this has a potential to make a few things a lot simpler. As for what core I'm going to use for this, originally my thought was to keep things as simple as possible, and for debugging, just write a very simple module which would allow me to write the internal program memory and reset the core, and that's all you really need, right? But after some discussions, on the Slack channel, it seems like, maybe something with JTAG support would be a little bit nicer to use, and we can provide standardized JTAG interfaces for debugging the cores. And the debug modules that are built into the core basically already have the capability of resetting the core and writing to the program memory, and they give you some more useful features on top of that. And they work with standard tools like GDB and whatnot, so you can just do you can use your make file to program this thing ideally. So, or I guess not just make file, but also if you have like a Eclipse setup or whatever, then that'll hopefully work. So what I'm thinking about doing now is, instead of using Pico RV32, which doesn't have a debug interface, is switching over to using VexRisk5, which does have a debug interface, and we can get that all integrated. So what I've been working on here is, kind of identifying the core and figuring out how it works and figuring out where it's going to sit in the setup. And we'll take it from there. So this will probably take a bit longer to get operational than some of the other stuff, but plugging away at that. And then once we get this operational, then it's going to be also, I think, a lot easier to port to additional FPGA boards, because we won't need to make modifications to the driver code and whatnot. So anyway, this should be interesting as this functionality comes together. All right, so another thing is, coincident with bringing up the Softcore, I've made a couple of changes to a couple of the other slides here. So for the PHY registers, I'm still thinking about adding some PHY registers that the driver can simply read, but what I'm going to do is limit this to just status registers. Any control over the PHY level components will be done through the management Softcore. So this will allow things to stay somewhat board independent. And the PHY registers here, basically, I'm just going to expose the most straightforward information. So, link capabilities and the current speed, loss of signal, auto negotiation status, block lock, and maybe FEC status, things like that. So not all that much, something that we can implement in a relatively standard way for most PHYs, and the driver can simply read that. So the reason I want to do it this way is, then if you have like a Zinc device where you don't necessarily need that additional board management Softcore, then you can still have some visibility into what the PHYs are doing. But I guess you could potentially also implement the Softcore even if you're running on a Zinc device for PHY level and transceiver level management. So depending on what level of capability you need, you can do one or the other. All right, and then we have the GTYPLDRP connections, and the main change here is that I don't think I'm going to be exposing these through the main register interface. I think I'm only going to connect these to the Softcore, and then all access to the PLL and GTY transceiver connections, that'll all be done through the Softcore. So as the upshot of this is that the software or the Softcore can perform arbitration. It can enforce all the proper sequencing, waiting for reset completion, things like that. So while it's bringing up, if you're going to change the line rate, you can make sure that while the transceiver is being reset, there's no other operations, poking at these transceiver channels that could, screw things up. Because there's, I know in the documentation, there's a couple of, big flashing warnings in a few places, like, don't access a DRP while the clock is not running, otherwise it can cause a DRP interface to hang. So the Softcore can enforce that and make sure that if the transceiver is currently in reset, that certain registers are not accessed. So so yeah, some of this. So yeah, I've also mentioned a few things about iScan and whatnot. So I have that working separately, but I have to get that integrated into the Softcore and get that set up on the board. So all right, so that's about it in terms of that. 10G25G switching. There's still a couple of to-do items related to this. I know Adam John has been working on this. We talked about that the last time. I think a good portion of that functionality we're going to try to push into the Softcore at this point instead of implementing directly in HDL, just because it'll make things a little bit easier to to extend and modify, and it's just in some sense easier to work with software. Since we don't have the core operational yet, I know Adam John has been working directly in HDL. The idea is we'll figure out all of the sequencing and whatnot, what registers need to be, written in what order, and what needs to be done in order to switch between one line rate and another. But then what we will do is figure out what interfaces need to be exposed, in addition to just the DRP interface itself, and then we'll port a lot of that over to run in the software. And it's possible some of it will leave in the hardware. I'm not sure what makes the most sense at this point. But there's also some other modifications that need to be made in terms of adjusting some of the transmit components to handle drop transmit packets, because right now that waits for the PTP timestamps. And well, if you clear out the transmit FIFO, then you don't see any of those timestamps and things get all kind of screwed up. So that's on my to-do list to take a look at, because we can't really reset the transmit side until I have that fixed. Actually, I guess maybe you could. You just have to have the Softcore, for instance, make sure that there's nothing in the transmit pipeline or in the transmit FIFO before resetting the transceiver. Not sure about that. I'll have to do some more ruminating. But the my thought for now is that we won't actually implement that until I have that reset handled correctly. All right. That brings me to the end of the presentation here. I'll put up my to-do list for the stable release again, because I know the folks at MLE have been asking about this. What do we need to do to get to a point where we can actually cut some version releases? So a few things have been checked off. Self-contained checksum offloading. I think as part of making some of the modifications to RSS, I'm going to be taking a look at that. Not sure at this point. Basically, the idea behind this is I don't want to be passing around a bunch of checksum command stuff. What I want to be able to do is just say, hey, this is an IPv4 packet, and then the NIC can just compute and insert the header checksum and the TCP or UDP payload checksum automatically at the appropriate offsets. So it needs to be sufficiently smart to know where those need to go in the packet and how to compute them. So yeah, I'm going to be looking at that because that's particularly important for running with RDMA, because you have to compute these checksums totally within the FPGA as opposed to the current checksum offloading, which involves the host networking stack quite a bit. And then I want to get variable length descriptor support. I mean, ideally, I want to get it completely working, but having it, at least things running with the new descriptor format, might be sufficient, because that'll mean less updates to the driver for the final full support for variable length descriptors. And then I also want to get the on FPGA management softcore operational. It looks like there's been movement on getting that coming together recently. So hopefully I'll be able to get that operational to the point where I'll be comfortable cutting an actual release within maybe the next month or two. So we'll see about that. I mean, the big thing is having the register space reorganization and the fine versioning taken care of, because with that I can make changes and bump versions and whatnot and prevent strange things from happening in terms of version conflicts between the FPGA code and the driver code. So that's kind of the main thing. I would like to get as much of this other stuff squared away as possible before I start actually cutting version releases. And then I notice we have Bob from Cisco on here. Once I get like the FPGA management softcore implemented and the variable length descriptor support operational, then I'd be more than happy to start looking at getting Corundum running on whatever hardware Cisco wants to send in my direction in terms of getting in terms of stuff that you want Corundum to run on. So that's yeah, that about rounds out everything that I have to present today. So if anybody has any questions or any points they want to discuss, go ahead and speak up in the chat or whatever. All right.
Hi, Alex. It's Bob.
Hey.
Hear me? Hi.
Yeah. How's it going?
So Yeah, you said the two things were the variable length descriptor, and then also the management,
The
the
softcore, yeah,
softcore.
yeah.
Yeah. So that's going to be, yeah, management softcore, similar to like an external BMC, right? Well, we don't have a BMC on our board. That's why.
Well, right. So the softcore, it's the idea is that it kind of unifies the interface across all the boards, right? So right now the driver has to be aware of, you know, where things sit on the various I2C interfaces on the board and how to talk to those and whatnot. But the idea behind putting this little softcore on there is that the driver can just say, hey, I want to read, you know, these bytes from, you know, QSFP number 1. And then the softcore knows how to, which I2C interface to use, how to set the muxes and whatnot to do that. Or the driver can say, give me the board MAC address, right? And well, maybe it's stored in an EEPROM, maybe it's stored in an external microcontroller, you know, the softcore knows how to do that. So yeah, so it's nice that your boards don't have, you know, an external microcontroller, because that makes things a lot simpler in terms of interfacing. But there's many different, you know, I2C buses on many different boards. Some of them use muxes, some of them, you know, use multiple bus segments to different modules. Some of them use module select lines. It's kind of a mess. So by hiding that behind a softcore and putting the softcore in the middle, then the driver can just always do the same thing when talking to a board.
Right.
And
It
that'll
makes
make it a
sense.
lot easier. Yeah.
So because there'll be differences in different boards, though, are you planning on having like a list that you have that says what's supported on each board? You know,
Yeah.
like, okay.
Yeah. Yeah.
Perfect.
Yeah. And then the other thing is that, you know, you can always, you know, return an error from one of these little API things. So if something isn't supported, you know, there is no onboard EEPROM, and you ask the software to read from the EEPROM, and it'll say, oops, we don't have an EEPROM, sorry.
Yeah.
And
Not
then,
found. Yeah.
yeah, exactly. Yeah. But
Okay.
the key point is having kind of a standardized API that you can implement for these things. So
Right. The driver doesn't have to do all that work to figure it out.
exactly. Yeah. Yeah. I mean, it's one thing to do board specific stuff in like the user space tools. You know, if we have to do that, you know, whatever. But I want to try and keep that out of the driver, because we might be at some point, you know, sending the driver upstream into the Linux kernel, maybe, or sending it upstream into DPDK. And if we have to modify the driver every time somebody adds a new board, you know, that just becomes a, you know, pain. So
Okay. So what about flashing? That's probably a bigger. We
flashing.
don't.
Well, flashing is a kind of a user space thing, right? Because you don't really need that to be rolled into the driver. So as long as the user space tool can talk to the board, then we can implement, you know, more specific stuff in the user space application for talking to the board.
Okay. So
The other thing too at this point is I don't have my head fully wrapped around how we're going to flash some of the Intel devices. I know the folks at the MLE are going to be using Intel devices for their boards, and I have looked a little bit at, well, so they're probably going to have to, you know, grapple with this at some point. I have looked a little bit about, you know, what goes on in the Intel devices in terms of, at least in terms of a couple of the boards that I have. It's, as far as I can tell, significantly more complicated. And I'm not sure if this just happens to be a board design thing and that it's artificially more complicated than it needs to be, or what. So it might make sense to involve the softcore in this at some point. Maybe it's going to be a requirement for the Intel ones. I don't know. We may need to kind of rework the firmware update tools to, you know, be aware of some of the things that need to be done for the Intel devices. I'm not sure exactly what that's going to look like at this point. What I can tell you though is that Intel has this like parallel flash loader core that they like putting on like a Max 10 FPGA that sits in between the flash chip and, you know, the main Stratix 10 or whatever device. And their flash chip can be divided up into a whole bunch of different partitions with different purposes. And I'm not really sure exactly what all these are responsible for. If some of these are, you know, I think some of them might be related to some of their, you know, bitstream security stuff. Yeah, I don't know. So on the Xilinx ones, it's great. You can just write the bitstream straight to the flash and you're done.
Yeah,
For
right.
the Intel ones, it's not clear it's going to be that simple. So yeah, we'll have to cross that bridge when we get there. But bringing up Flash programming, that is probably something that we should discuss at some point, because it would be great if we could be able to cross Flash between Corundum and the Cisco firmware. So I'm not sure if that means adding support for the Cisco firmware to the Corundum tool and the Corundum format to the Cisco tool, or if maybe the Cisco format is flexible enough to where we can just use that one for both. I'm not sure. So I've definitely had some people asking about that. They got like one of the Cisco boards, like, okay, how do we update the firmware on this? I'm like, yeah, you need a JTAG cable.
It
But
shouldn't be that, it shouldn't be that hard. I mean, I think it's
yeah, I'll have to take a
the
look at
base
the
64
format.
encoded stream, I think, that we use. So that we just take the bit file and make a base 64 encoded stream, I think. And so
Right,
maybe we
right.
can just play around with changing
Yeah,
them
I
back and
think
forth.
right. So I think that part's not too bad. I think there was maybe some metadata or something that you might need to have attached so the tools know
Oh.
what board is on the other end and whatnot.
Yeah,
I was taking a
could
brief
figure
look
that
at the open source repository that has that that code in there. At least I was looking at the firmware update tool, but I either didn't find or it isn't included in there the actual tool to generate that that code, so, or to generate the files. So I'll take another look at some point. This has been a very back burner thing for a while.
Oh yeah.
I was like, before I was talking to you guys, that was one thing I had in the back of my head. It's like, it would be cool to support, the Exablaze firmware format. So, I guess the other thing we could do is generate the format that your update tools are happy with. So then you guys wouldn't have to make any
Right.
modifications for that, but we
That's
could
not-
say, okay, we'll generate that from the Corundum bit file, and then you can use those tools to load it when you're running that firmware. And then to switch back, we can have the Corundum firmware update tool support the Cisco format, so you can switch back. So anyway, that's kind of a long-term thing to get the details on that sorted out.
Yeah,
But
maybe
ultimately,
I
don't think it'll be that complicated. Yeah.
Right. Not until you start testing and we get, so you have two other things to do at least before we get you the boards, and then we start.
Right.
That
Right.
kind of
That's
stuff.
true. Yeah.
All right. Thank you.
Yeah, no problem. All right. Anybody else have any questions or comments?
Just a quick one, I guess.
Sure.
The completion queue manager. No, actually, the queue manager. I guess that's the
Right.
module that's used in all over the place, right?
Right, yeah.
So will you revisit this while introducing more changes to the variable links descriptor field change process, or
what
is this
about the
kind
queue
of
manager?
fixed? Will you visit this while updating the data path to accept variable descriptor sizes, or is this fully out of the scope in this case? Just to make sure we don't do edits at the same time in there, because we need to visit this for the Intel optimization path.
Well, okay, so let me tell you, let me say this. I'm going to have to make a couple of modifications to how the pointers are implemented in there, because
Okay.
right now they're implemented in terms of increments of descriptors, but I need to change that to some fixed block size. But that should be a relatively small set of changes. But for the full variable length descriptor support, that module is basically going to be completely rewritten. So
okay.
Yeah. So that's why I'm like, yeah, I don't really want to do too much to that module because I'm going to be rewriting it. But I think it's a reasonable stepping stone to make a couple of these changes now, because then we can use that to kind of facilitate the development of the rest of the variable length descriptor support hardware. Because basically we can migrate to using effectively the new descriptor format on the driver side first, and then we can work on getting the hardware updated to actually fully parse that. and that we have a good idea the driver is actually doing the right thing because we can run with that partially implemented format. And then once we get it fully implemented, then we can update the driver to actually generate variable length descriptors instead of fixed length ones with the headers attached. So
yeah, makes sense.
yeah.
Okay, so
keep you guys in the loop when I need to make any changes to that. But it sounds like you guys you need to make some tweaks for this thing to build properly on Intel devices, right? You're mainly looking at inferring the correct RAMs for stuff. Or
yeah, well, I guess the thing in this module is that there is like at least one path, maybe more, that are kind of asynchronously hooking up to RAM structures, and that doesn't really get timing.
Yeah,
so
and unfortunately, there's not really much we can do about that, because if you do add registers in there, then you're going to have to be handling things like every other clock cycle or something. So yeah, I'm not sure if there's a good solution for that.
Yeah, I guess we have to think about it, because that won't scale this way, I guess. So this is really not the way Intel requires.
So this is a limitation of the Intel M Labs or something, or what problem are we running into here exactly?
Yeah, so they require the registers on each in and output signal of the RAM, and that also refers to write enables, for example, not just address and data. So everything needs to be registered. Otherwise, it couldn't pack this.
Right, but this is just
they physically are required, right? by the fabric. So it's not not a software tool issue, but the fabric requires this because it's built this way.
Wow, that really makes the distributed RAM a lot less interesting on the Intel devices. You need a whole bunch of registers everywhere. Interesting. Okay.
Yeah, I guess from a timing perspective, in this case, it makes sense anyway. But yeah, you're right.
I mean, I understand it for block RAMs, maybe, but I mean, the whole point of the distributed RAM is that it's literally just a LUT, right? So you don't need to register before every single LUT. So why would you need to register when you're using a LUT as distributed RAM? That doesn't make any sense.
Well, yep. Now, really, yeah, I guess that's combined in combination with their routing infrastructure. So they have a little differences than they have in place on the designing side. So I guess that may play into this here as well. However, that's just how they are built.
Right,
so
right,
we can
yeah.
argue about that, but I guess we can change this.
Yeah, so the question becomes, how do you work around that problem? Yeah. Well, so I mean,
exactly.
I guess it works right now. It just it's a timing issue. Well, so what happened in that case? It just used flip-flops for all of that state instead of putting it in distributed RAM? Is that what happened? Or did it put it in block RAM?
Actually, not sure. So I just had a look
Okay.
at the inferred RTL yet and timing. So I just checked the path that was created by the tool, but I need to check what it actually implemented in this case.
Right. Well, I guess you can look at the path and see what it's going through. If it's going through a couple of block RAMs, then you know it inferred block RAM. If it's just going through flip-flops, then yeah.
Well, then timing would be good, I guess. Yeah. Okay. So I guess we'll put a little thought in there, and then we can I don't know, have a joint look on this one. So
yeah, we might need to do something like that. I mean, these kinds of restrictions are definitely good to be aware of, because that may drive, the design of some of the other components, right? Because down the road, I also need to for the new descriptor handling logic, I'm going to need to do some similar stuff. I'm planning on using a lot of distributed RAM for that. So,
Yeah.
if I can make sure I'm doing that in such a way that it's actually going to infer correctly on the Intel devices from the get-go, then that's going to save a lot of headaches.
Yeah, so exactly. So that's kind of the idea why I wanted to talk about this one, because I guess we will kind of this week hopefully provide some patches for a couple of modules, and basically we could use this as examples for new code to be written.
Yeah, that sounds good. Yeah, if we can figure out what needs to be done, because the main thing that I was looking at the last time I went through is just adding some of the, directives that actually allowed Quartus to infer some of the distributed RAM. But because those definitely helped. So I guess in those cases they had the necessary registers or whatever. But in a few cases, yeah, I guess we're going to have to make some more extensive modifications. So.
And you were actually right. So
it
definitely inferred block RAM. So it says here Altera Zinc RAM implementation RAM block. So it's the block RAM path that it inferred, and the timing path is from block RAM to block RAM.
Well, okay, so I mean, we're expecting a block RAM in there anyway for the QState. So, because the thing is, there's like two different pieces of state in there that should be stored in some kind of memory, right? One of them is all of the QStates, and the other one is kind of the active QStates, right? So the QStates are definitely going to have to go in block RAM because you could have a large number of Qs, but the smaller table of queues that are currently being worked on, that is supposed to go in distributed RAM, or that's my intention anyway. So if both of those ended up in block RAM, yeah, that could definitely be a timing problem.
I guess that's what happened. Yeah.
Right. Okay.
So
yeah,
we'll hammer a bit on this one, and then
yeah,
we can have another chat about this, I guess.
Yeah,
there won't be a solution today, I guess.
Well, actually, just a quick question about the boards that you guys are putting together with the Intel devices. How are you guys planning on doing the firmware update for those? Have you guys looked into that in much detail? I mean, it says it came up a couple minutes ago.
Yeah,
I'm assuming you just directly connected the QSPI flash to the FPGA, right?
Well, directly in this case means via this SDM, right?
Well, right, but you didn't stick another FPGA on the board, right?
No.
It's directly connected to the, yeah, okay. Right, so, yeah, so obviously you can't directly poke at those pins. You got to go through the SDM, but that's just kind of what you need to do, I think. Okay.
And other than that, I guess currently we think we will use CVP. So that's
okay, I see.
Kind of also a nice way to kind of go away from having a lot of firmware updates flashed onto the card, but rather.
Well, CVP has advantages and disadvantages. The disadvantage is now you also need to have your bit file sitting on the host system somewhere where it can be loaded by the driver at some point during the boot process. So, yeah, I guess I'm just thinking Xilinx doesn't really have a direct equivalent of that. They have their tandem configuration, but that's basically just a bastardized version of partial reconfiguration.
Yes, and I guess that's what was the other name? Autonomous mode, I guess, was the Intel equivalent. Or maybe I mix it up. So I guess
okay. So there's a couple of different things. I think the Intel autonomous thing, you're still loading the entire bit stream from flash, but the idea with autonomous is that it releases the PCIe logic from reset before the whole design is loaded. I think something like that. But Intel can get away with some of these tricks because all of their PCI Express stuff is in hard logic versus Xilinx uses soft logic to connect the PCIe hard IP to the transceivers. So, you know, because of that, for Xilinx, you have to do partial reconfiguration just to bring up PCIe, which, you know,
Yeah,
it has
it's,
advantages and disadvantages. The advantage is more flexible on the Xilinx ones, but the disadvantage is, you know, you have to deal with partial reconfiguration.
yeah.
Yeah, I guess that also probably makes the CVP a lot more reliable, right? Because all you need for that is the PCI Express block configuration. I think you can load pretty much everything else. Versus for the Xilinx ones, you know, what sits in the flash has to properly match what you're loading over PCIe, which is, you know, in my opinion, less than ideal, but, you know, it is what it is. All right, let's see. Is there anything else to discuss here? Anyone else have any questions, comments? Oh, did we lose? Oh, we didn't. I thought we lost somebody. Okay, now Ulrich is still on here. Any other questions, comments? Nope. All right. I guess with that, we'll go ahead and end the meeting for now, and we'll see you guys in a couple of weeks. If you have any other questions, you can ask on the Slack channel or whatever. Thanks to everyone for joining in.
Okay, thank you. Bye.
All right, talk to you.
Thanks for your time. Bye.
Sure, talk to you.